All right, welcome to The Explainer. Today we're diving deep into a modern sci-fi masterpiece, Interstellar. We're going to peel back the layers and figure out just where the mind-bending science ends and the movie magic begins.
So this was the big rule, the promise from the get-go. Kip Thorne, a Nobel frickin' laureate, was the science advisor. He said everything had to be grounded in real physics. So, the wildest stuff in the movie, it had to at least spring from actual science. A pretty bold claim, right? Okay, let's see how they did.
First up, the science of survival. So the whole movie kicks off with a really grim picture. Earth is, well, it's dying. There's this mysterious blight, this plague, that's just systematically wiping out all of our crops. It's a race against time for humanity.
And here's the thing. To make sure this felt real, they actually talked to biologists. And the verdict? While a blight this aggressive and widespread has never happened, they couldn't scientifically say it was impossible. So, with that terrifyingly plausible threat hanging over everyone's heads, the mission is set. Find a new home for humanity. But to do that, you've got to take a shortcut, and this is where we get into some really cool physics.
Okay, Section 2, a shortcut through space-time. So, how do you travel light years away without taking, millions of years? The movie's answer is a wormhole. And get this, it just appeared. Right there near Saturn, like a cosmic doorway waiting for us.
Now, this isn't just movie nonsense. The idea of a wormhole, or an Einstein-Rosen bridge if you want to get technical, is a real theoretical concept. It's legit a passage through space-time. But, and this is a big but, this is really the first place where you can see the science bending to fit the story.
Here's the breakdown. In theory, if wormholes exist at all, they'd be wild, super unstable. Like they'd probably collapse the instant they formed. You couldn't even send a probe through, let alone a spaceship. But in the movie, we get this perfectly stable, perfectly traversable tunnel, just waiting for us. The film's explanation is that some advanced civilization, maybe even future humans, built it and left it there for us. It's a huge speculative leap for sure, but it's one that the entire story depends on.
All right, next up, the Gargantua paradox. So once they're through that wormhole, our crew comes face to face with the star of the show and also its biggest, baddest villain, Gargantua. It's this enormous, spinning, supermassive black hole. And somehow, there are planets orbiting it, potentially habitable planets, which is a lot to unpack.
The first stop is Miller's planet. It's a water world, but it's not exactly a beach paradise. It's home to these absolutely colossal tidal waves. And this planet, man, it perfectly highlights that constant push and pull between what's scientifically possible and what just looks awesome on screen.
So let's break this down. In reality, the tidal forces from Gargantua would create these huge but kind of stationary bulges of water, and the planet would get tidally locked almost instantly, meaning one side would always face the black hole, stopping any regular waves. But in the movie, we get these massive, mountain-sized waves that come crashing down every single hour. It's pure, nail-biting peril for the astronauts. Even Kip Thorne admitted they took some creative liberties here for dramatic effect, calling it a rare, solitary wave while basically winking at the camera.
And then there's this number, 60,000. That is the insane time dilation factor on Miller's planet. For every single hour the crew spends down there, 7 years pass for everyone else. Just think about that.
So where did this crazy number come from? Well, it turns out this was a non-negotiable from the director, Christopher Nolan himself. He needed those gut-punch emotional stakes, so Kip Thorne went back to his calculations and figured out, okay, it's just barely possible, but only if Gargantua is spinning at a speed that's right on the edge of what's physically possible. So again, we see science getting stretched and warped a bit to serve the story.
And what about that beautiful glowing ring around Gargantua? Well, a real accretion disk would be deadly. We're talking millions of degrees, lethally radioactive. You wouldn't be able to look at it. It would also look super lopsided because of the Doppler effect. But the movie gives us this clean, cooler, symmetrical disk that provides just enough light and heat. Why? Because as they said, they didn't want to totally baffle the audience. It was a conscious choice. Sacrifice some hard realism to keep us focused on the human drama. But why keep making these compromises?
And that question leads us right here, the Nolan effect. We have to talk about the man himself, Christopher Nolan, and his very specific way of making movies. A way where the science is amazing, but the feeling, the emotion, that's always king.
Think about his movies. You've got these puzzling narratives, time all twisted up, complex suspense, stories woven together. But at the center of all of it,
Every single time, there's this deep, powerful emotional core. Nolan is a master of the narrative maze, yeah? But his films are just as much about psychology and feeling as they are about the crazy plots. And that's the key here. All those scientific compromises we talked about, they're all in service of the story's heart. That insane time dilation, it's not just a cool physics lesson. It's the absolute tragedy of a father watching his kids' lives flash by in the blink of an eye. In fact, get this, when Hans Zimmer was writing the main theme, Nolan didn't tell him about the sci-fi or the black holes. He just told him a story about a father having to leave his child. That proves it, right? The emotion came first. Which brings us to the film's biggest, most out there idea, love as a fifth dimension. This is where things get really profound, maybe a little controversial, where the why of the story, the emotional motivation, literally becomes a physical force in the universe.
It all boils down to this one question, posed by Brand in the film: is love the one thing we know of that can transcend time and space? And with that one question, the movie shifts gears. It's not just hard sci-fi anymore. We've officially entered the philosophical deep end.
As Brand says, love isn't something we invented. It's observable, powerful, it has to mean something. She even speculates that maybe it's an artifact from a higher dimension. Now you might think that's just some pretty poetry, a nice sentiment, but no. In this film, that idea becomes the actual, functional mechanic for the entire climax of the movie. So Cooper ends up inside the Tesseract. It's this wild, four-dimensional space that future humans built so he can interact with his daughter Murph's timeline. But think about it. Her entire life is laid out like a library of moments, an infinite sea of time. So how in the world does he find the one specific moment he needs to save humanity? Well, the movie's answer isn't in a physics textbook. It's in a feeling.
Here's how the movie puts it all together. Step 1. Future humans build the Tesseract. Step 2. They need an anchor point, a way for Cooper to find the right spot in all of space-time. Step 3. That anchor isn't a number or a coordinate. It's the incredibly powerful, enduring love that Murph has for the father who left her behind. And finally, Step 4. In the world of Interstellar, love becomes a quantifiable force. It acts like gravity, pulling him to that one crucial moment, letting him send the data that saves everyone. It literally bridges the dimensions.
So, in the end, that's what Interstellar's all about. It's not trying to be a physics documentary. It's using the language of physics, wormholes, black holes, relativity, to explore something deeply, deeply human. It's about the connections that bind us to each other across any distance, even across time itself. It's not a fight between science and story. It's science being used to tell one hell of an emotional story. Which leaves us with a pretty incredible thought, right? If a story can use love to bend the rules of space-time, what other human forces, what other emotions could bend the laws of physics? You know, that's the kind of question that keeps us looking up at the stars and also looking inward at ourselves.